No, the pencil isn't really bent, although it appears to be. And physics teacher Bruce Illingworth in the pool doesn't really have his head displaced as it appears. The explanation for these strange appearances involves changes in the speed of light. Here we see a ray of light entering a pane of glass at an angle. The speed of light in a vacuum we call c constant. It's nearly c in air, but its average speed v inside the glass is considerably less than c. We see it emerges from the glass parallel to, but somewhat displaced from its initial path. Light changing speed from one material to another gives rise to refraction, the subject of this lesson. If you roll a pair of cartwheels down a slight incline from sidewalk to grass, the wheels roll slower on the grass than on the sidewalk. Why? There's more interaction of wheel surfaces with grass than with the smoother sidewalk. If you roll the wheels at an angle, so one wheel meets the grass while the other is still on the sidewalk, the wheels will swivel from their straight line path. Due to the change in speed, the direction of travel changes. Likewise with light. Here we see wavefronts of light heading toward water. Light travels slower in water than in air because there's more interaction with the denser water than with thinner air. The wavefronts in this diagram represent wave crests of light. You can see how the wavefronts swivel when they meet the water surface. They bend from their original course. We say their rays are refracted. Note that the direction a ray is moving and its wavefront are always at right angles to each other. Notice another thing. The distance between wavefronts is less in the water. Interesting. The wavelength of waves is somewhat compressed. But another thing, the frequency of the waves remains the same. Important to know. The angles of incidence and refraction are measured from the normal. Here we see the angle of refraction is less than the angle of incidence. Look at the path of light as it enters water, reflects from a mirror, and exits the water. Light bends toward the normal in passing from air to water, and reflects from the mirror with an angle of incidence and angle of reflection the same. Note that when it exits the water, light bends away from the normal. How about speeds in this case? Does light change speed as it travels from air to water? The answer is yes, it slows. Does light change speed as it reflects from the mirror? The answer is no. Reflection does not involve changes in speed. Does light speed up as it exits the water? What's your answer? I hope you said yes. Just how much the speed of light differs from its speed in a vacuum is given by the index of refraction, n, of the material. N is the ratio of the speed of light in a vacuum to its speed of light in material. For example, the speed of light in a diamond is 124,000 kilometers per second. And so the index of refraction for diamond is 2.42. For a vacuum, n would be 1. In the same material, light of different frequencies has different speeds, different indices of refraction. Frequency plays a major role in a diamond. Here we see a sample ray of white light entering a diamond. Violet light is slowed more than red light, so refraction is greater for violet than for red. Violet bends more than red. Other colors in between aren't shown here. This difference in refractions produces the variety of colors that make diamond jewelry special. We see the rays of light reflecting twice from the bottom of the diamond, where light undergoes what we call total internal reflection. I'll defer this topic to your textbook. What's important here is that the different colored rays emerge well separated. A violet ray that reaches your eye is displaced from a red one. So if you see a sparkle of violet, you won't see a red sparkle unless there's movement between the eye and the diamond. The quantitative law of refraction involves a bit of trigonometry and is called Snell's law, credited to Willebrord Snell, a 17th century Dutch astronomer and mathematician. It's n sub 1 sine theta sub 1 equals n sub 2 sine theta sub 2, where n sub 1 and n sub 2 are the indices of refraction of the media on either side of the surface, and theta sub 1 and theta sub 2 are the respective angles of incidence and refraction. If you know the two indices of refraction and one of the angles, you can find the other angle. Or if you know both angles and one of the indices of refraction, you can find the other index. Perhaps in the lab part of your physics course, you can play with Snell's law. Yum stuff. Note here how refraction accounts for seeing a fish to be nearer the surface of water than it actually is. Because you're accustomed to seeing light following straight line paths, you place the fish closer to the surface. If you're spearing fish, you'll want to know about this. Note also that due to refraction, the full root beer mug appears to hold more root beer than it actually does. Sample light rays coming from the root beer refract toward the viewer's eye. The result, a fuller looking mug. When the mug is partly in water, what's happening? Aha, light from the mug through the water doesn't speed up as fast as when through air. With less refraction, we get a better view of the amount of root beer in the mug. Yum! Refraction accounts for the moving patterns of bright and dark areas at the bottom of a swimming pool. Parallel rays of sunlight on the pool become non-parallel when refracting from an uneven, bumpy water surface. Just as we see the pool bottom shimmering, a fish looking upward at the sun would see the sun also shimmering. Because of similar irregularities in the atmosphere, we see the stars twinkle. Refraction is yum physics. Atmospheric refraction accounts for mirages. Light travels a bit faster in hot air than in cooler air, so if the air near the ground is warmer than the air above, as it is in desert in the daytime, light from the palm tree refracts upward, which is to say, bends upward. Your eye interprets this as a reflection, when it is really refraction. Light from a distant blue sky that refracts upward in the same way gives the illusion of water not far ahead. Many a thirsty person wandering in the desert has mistakenly seen a cool pond ahead. Sorry, no refreshing drink. This is more common on roads, where air warmed at the surface produces the same effect. Whenever we look downward and see sky, it's either reflection or refraction. Sometimes the two are confused. Here's an interesting application of no refraction when there's no change in light speed. My niece Stephanie holds a glass rod about to be submerged in a container of vegetable oil. You see the rod in air, actually its edges. But when the rod is submerged, the glass doesn't show. You don't see its edges. It's invisible. So the question I leave you with is this. How does the index of refraction for the glass rod compare with the index of refraction of the oil? Until next time, good energy.